So I wanted to give a simple demonstration of how to speed up Go programs and kind of a rough introduction to concurrency, Go routines, wait groups, a few other things that people often use and why you would use them, or at least some examples. So here we have a very simple program. We basically have this function slow file download, which takes a string and returns a string. I'll explain what it does in a moment. But the way you can think about this fake program, I want you to imagine that you want to download 4 files from, let's just pretend they're on 4 different servers. The names don't really matter, these are just example files, but let's just pretend these are 4 files, 4 URLs on 4 different servers, and you basically just want to download all of these files to your local computer, and you just want to write a Go program to do that. Well, if you were to run this program as it stands, or I guess I should specify, what this is doing is we're storing a list of files we want to get, walk through each of the files, and then we're going to print a response from this slow file download function. So you can pretend that what this function is doing is a really expensive and slow network request, and then when it eventually gets the file successfully, it returns a little message saying, yep, we got the file and it took us n many seconds to get it. But to simulate slow servers instead of actually doing any network requests, this is just going to sleep a random amount of time. And it's meant to simulate just some slow network requests with some varying time. So it makes more sense if you look at the output. So let's just run this program really quick. So this is just going to start downloading files, and you can see that it's telling us how long it takes. And obviously this is taking a very long time because all these files are downloading sequentially, meaning that for the first file we start the download, it's going to wait a random amount of time. In this case it was 1 whole second, so it sits and does nothing for a whole second, then eventually pretends to download a file and then returns our message saying that we got it. And it does this for all the other files. So first we're going to wait 1 second, then we're going to wait 3 additional seconds, then 4 additional seconds, then 2 additional seconds. So we can actually time this using the time command, at least on my machine. All this is doing is telling me how long go run main.go is going to take. So if we run this again, we can see that this is going to be really, really slow. So I'm just going to wait a minute and wait for this to spit our output. Oh, this is taking a while. Do 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 do. Okay, so this took 20 entire seconds, extremely slow. Especially if this was a part of a larger program, you can imagine how ugly this would be. And the reason is because each one of these downloads is being waited for independently. So this 19 seconds represents the sum of all of this. So we wait 5 seconds, then an additional 5 seconds for 10 total seconds, wait an additional 5 seconds for 15, and then 19, plus a little bit of extra for starting up this whole program. So that's obviously very slow. So you may have heard or wanted to play around with Goroutines to make this faster, so you may be tempted to just take this line of code and put it inside of a Goroutine, which looks something like this. Create an anonymous Goroutine, execute it, and then just move this line of code into the Goroutine. You may have been tempted to do something like this. And so, at least on the surface, this looks like a good solution. You're creating a list of files you want to download. For all the files, create a Go routine and go do this. But if you actually run this, you will see that it does nothing. And in fact, it will always do nothing. It will do nothing forever. It doesn't matter what this other function is doing, this slow process. It could be curing cancer for all we know. It's going to almost always, if not always, exit prematurely for a very obvious reason. And you have to understand how Go works to understand why this is happening. When you run a Go program, it looks for the main function and it begins executing. So it goes here and it creates a list, or rather a slice of file names, walks through the list of names, begins to start up a Go routine for each of those 4 files, which is extremely fast, fractions of a second. But this setup procedure is very quick. So it sets up these go routines on separate threads, but then it's done setting them up and it exits this loop and then it's done. So the main thread has finished. And in Go, when the main thread finishes, the program is done and everything is killed. So this will always fail. So this is not a good solution. This is always going to fail, and the reason is because the main thread, once it actually sets up the go routines, which again is very fast, this is extremely fast, fractions of a second, it's going to set them all up. It's then going to be done setting them all up. Then it's going to be done with the main function, which is synonymous with the program exiting, so it just exits. So what we really want to do is force the Go program to wait until these results come in. And there is a naive solution to that. We can explicitly force the main thread to sleep for a really long time. So let's wait like 20 seconds, right? So now all we've changed by adding this sleep statement is that once it sets up the go routines, it's now just going to sit here and do nothing for 20 seconds without quitting. And now let's see what happens. Well, now we start getting our results in. They start executing. But you'll notice that here at the end, we're now sitting here and doing absolutely nothing, just blocking and blocking and blocking until it eventually finishes, which is obviously not what we want. What we want is a way to wait for these go routines to finish, and then as soon as they finish, just give up and just stop. And so how do we accomplish that? Well, one way we can accomplish that is with a wait group. So a wait group, let me just declare the variable first. Sync.waitGroup. A wait group is a data structure. It's imported as part of the sync library, hence the sync.waitGroup notation. A wait group is basically just a counter at the end of the day. It's just a counter used to count go routines. It just counts them for us. And wait groups have a nice functionality where they will wait until the count reaches 0. So this line here, creating a wait group, is basically telling Go, listen, I'm about to create some go routines. I would like to count them, and I would like you to wait until the count reaches 0, meaning that the go routines are finished. Well, right now, if we were to stop here, we haven't actually added anything to the wait group, so there's nothing to wait for, so it's just going to fail. We need to explicitly tell the wait group to wait for something, and then eventually tell it that it's done. That's what these 4 lines do. So there's 4 additional lines we need. 1, 2, 3, and 4. And let's walk through what they do. So when this program executes, Go is going to look for the main function. It's then going to create a wait group, which is just a counter of Go routines. It's then going to create our slice of file names, walk through the file names, and this wg.add1, what that's going to do is say to the wait group, it's going to say, I'm about to start a go routine. So increment your count by 1. So now we have 1 process that we need to wait for. Then we're going to set up the go routine, and we'll get back to this defer statement in a moment. Then it's going to run again on the next string, on the next file rather, and say, hey, I've got yet another thing I want you to wait on. And then I've got yet another thing I want you to wait on, and yet another thing I want you to wait on. So eventually the wait group count is going to reach 4, because it's going to represent 4 go routines I want you to wait until they're finished. But we actually need to tell the wait group when these go routines are finished. That way this count can go down. Because so far all we've gone through is increasing the count. I want you to wait on 1 go routine, 2 go routines, 3 go routines, 4 go routines, but I need to actually tell the wait group, okay, I've finished, we can safely mark one of them as done. And that's what this defer wg.done is going to accomplish for us. This line is basically undoing this line. This is going to say wait for one more process, and this defer wg.done is going to say okay, you can decrease by one because at least one of them is done. The defer keyword in Go, this is basically saying eventually mark one of them as done. And the eventually in this case is going to execute when the code reaches right here, which is conveniently right after the Go routine finishes, this slow process. So just going back top to bottom, create a count of Go routines that haven't finished yet. So far it's 0. Create a list of files we want to download, walk through those files, tell the wait group we have one Go routine, we're adding one Go routine we want to wait on, actually build and run the Go routine, which is going to do this very slow process of downloading the files. And then once that finishes, once we reach here, this will get triggered, defer wg.done, which is going to say, ah, yes, I need to mark one of the Go routines as done. So as this program executes, wg.add, this is going to go up to 4 really fast. This is just going to immediately, as it walks through this list, wg.add is going to happen very quickly. And it's going to get all the way up to 4. And then slowly but surely, as these Go routines finish, they'll get decremented slowly. So it'll go from 4, it goes up to 4 very quickly, and then it very slowly goes from 4 to 3 to 2 to 1 and then to 0. Or sorry, from 3 to 2 to 1 to 0. So this 2 lines of logic, wg.add1 and then defer wg.done, is basically saying immediately add one Go routine to the wait list, and eventually, once it finishes, once the Go routine finishes, mark one of them as done. It's like a checklist. And this wg.wait is just going to sit here and wait for the wait group to go from 3 to 2 to 1 and eventually to 0. And once it hits 0, we can exit. So the wait group is going to start at 0. It's going to very quickly reach all the way up to 4. The Go routines are going to run in the background, and it's immediately going to hit this wg.wait with a count of 3 or a value of 3 because it starts at 0, so it's 0, 1, 2, and 3, and it's just going to sit here and it's going to be waiting on 3. And eventually one of the Go routines will finish, it'll get decremented, then it's waiting on 2, then down to 1, and then eventually down to 0. And now if we run this code, it should be significantly faster. So here, you're seeing a lot more come in really, that was significantly faster. And notice we didn't wait 5 plus 3 plus 3 plus 1 seconds. We waited much, let's time that so I can show you better. Let's reset the screen first. Go run main. So notice that the total amount of time taken was 4 seconds. That's the total amount of time this entire program took, and the reason is because it only had to wait for the slowest file to finish, which was 4 seconds. And if we run this again, we will continue to see this pattern where the wait is always going to, the total time rather, is always going to be the time it takes for the very last guy to finish. And we can just keep doing this over and over again. Because as these threads finish, they decrease the wait count and eventually it reaches 0 and then it's done. So it's always going to take a very short amount of time. So this is already significantly faster. We are now downloading these files all at the same time, and it's only ever going to take the slowest file amount of time. It's never going to exceed this value. Great. There is another way to solve this problem, or rather, there are other problems in concurrency than this. So far, this example that we're using Go routines with, this is when we care about everything finishing. But there are circumstances where we actually don't care that everything finishes. We simply want to get the first result that we can. So let's change this up a little bit. And let's say that instead of a slow file download, let's say that we're trying to download just one file, but we have a bunch of mirrors it might be stored on. So this might be a Google mirror. So let's just say you want to get a file, let's just pretend for a moment that the file is really important to your program, but you don't really care where you get it from. There's a couple different places it could be located. So it might be on the Google domain, it might be on, I don't know, the Debian domain, maybe Fedora has it. I guess Debian is debian.org. Or maybe it'll be hosted on Bing, which is hilarious. So now we simply want to grab this file from the very first person that's able to give it to us. So in this case, this is not a list of file names, it's a list of mirrors. And so now what I want to do is I want to get this file. It's the same file on 4 different websites, and whoever can give it to me quickest, great, we'll just go with that one. So here we're going to do a slow file download again. We're going to download the file we care about, or rather we're going to download it from the mirror that we want to get it from, and whoever gives it to us first, that's the one we're going to go with. And you can dream up scenarios where you may want to do this, where you're just trying to get a single piece of information, but it might be hosted, copies of it might be hosted in a few trusted places. But obviously, depending on where you are in the world, some servers are going to be faster than others. So you just want to get it from the fastest one. So what this is doing is basically saying, go through all the mirrors, try to download the file, and whichever one gets it to us first, that's the one we're going to go with. So what would that look like logically? Well, the way that we could do that is using channels. So we're going to modify this function a little bit, and instead of returning a value, we're going to have this function communicate over a channel. So instead of returning a result the way functions normally do, we're going to have it simply write the result to a channel. So in this case, succeeded is going to be a channel of type string, and instead of returning that data, we are going to write the result to that channel. So it looks a lot different than what you're probably used to, but all you really need to understand is that channels are simply a message passing scheme where you can simply send data between threads. So this is your main thread, and this is some other thread we're running on a Goroutine. So instead of returning the result, we're just going to write it to a channel. And to actually keep track of that data, we need to store the channel. So whoever is first is going to be a channel. We're going to make a channel of type string. We're going to use a Goroutine to run our very slow function, and we're going to add the channel to the parameter list, which is whoever is first. And what we can do, so far all we've done is set up the Goroutine, and it's going to send a message, but we're not listening for it yet. Right now, the slow file download function is going to write to this whoever is first, but we're not listening for it. So we need to actually explicitly listen for an answer, and we do that with a select block. And I'm going to explain this notation in a minute. It's going to look a little complicated. So here, what this block is basically saying is, first we create a channel to talk on, whoever's first. It's just a string. We have a list of mirrors that we could potentially download this file from. For each of those mirrors, start a Goroutine to try to download the file as fast as you can, and we're going to pass in the mirror where we want you to look. So in this case, it would either be Google or Debian or Fedora or Bing, and then you're going to write your results to whoever is first. And this block down here, this select statement is saying basically start listening on a channel, or start listening for channel responses. And this case m:= arrow notation, whoever is first, is basically saying we have this thing m, it's just a variable. Its name doesn't really matter, we're just going to call it m. It's listening for the output on whoever is first, which is being written to here. It's a different name, but it's the same variable. So whoever writes to this, it's going to get received here, stored, and then printed. So let's see what that does. So Bing finished first. It only took 2 seconds. So let's add a little bit of information. Let's see how much time the other ones are taking. So let's print a quick message. Let me fix my output here. It is going to take seconds. And so now, if I run this program, I will get to see how long they're all going to take. So Bing's going to take 4 seconds, Fedora is going to take 4, Debian's going to take 5 seconds, Google's going to take 4 seconds, and the first one that came back was Google. If I run this again, Bing is obviously the fastest, so Bing's going to come in first, and so Bing is the one that finished downloading. Let me actually separate this to make it a little easier to see. So Fedora and Google are tied for first place at a single second. And so whichever one of those happens to come in first, it doesn't really matter. But whichever one is fastest, that's what came back. And so this line represents this input. The message got passed in, whichever is first. But what if I actually want to get all of the results? I don't just want to get the first one, I want to get all of them. Well, you could just put this in an infinite loop. And now this will just continue to listen forever. But there's something interesting that happens when you do this. So here, because I've put this in an infinite loop, it's just going to continue listening forever for messages coming from this function. So it's going to wait for all of the mirrors to return a result. But here, when I run this, they're all going to come in, which is what we're expecting. So all 4 of them eventually return a result, but we got a warning, an error actually, that we hit a deadlock. And the fatal error we got is that all the Goroutines are asleep, so we're in a deadlock. What Go is warning us about, basically, is that remember that this is blocking in an infinite loop. It is listening forever for messages. But remember that we only started up 4 Goroutines, representing the 4 mirrors we're looking at. Eventually, they're all going to return a response. They're all eventually going to return. So once all 4 of them finish, there are no more Goroutines running anymore, but you're still sitting here listening forever. And you're listening for a message that's never going to come, because once the 4 messages come in, once the 4 Goroutines finish and send their results, you're still sitting here listening because you put it in an infinite loop. And Go is basically saying, hey, you probably shouldn't do that because you're waiting on something that's never going to happen, so it's a deadlock. And there is a solution to this, and the solution is to use a timeout. And a timeout is just like what it sounds like. It's a maximum amount of time you're willing to wait, and eventually you'll give up. And so what we can do is add a timeout to this program to basically say, yeah, go look on these 4 websites, it's slow, go do it, but stop listening after n many seconds. Just after a certain amount of time, just stop listening. That way this does not sit waiting forever. And here's how you accomplish that. You just declare a timeout variable with time.after, and you pick a timeout. Let's pick 15 seconds. And now we simply add a new case. And then return. meaning break out of the program, just give up. So now what this is going to do is we're going to sit infinitely and we're going to wait, and we're going to get one of two kinds of responses. We're either going to get valid responses from whoever's first, which is the results from the slow file download function, and it's going to infinitely listen for that, and it's also going to infinitely listen for the timeout. And the timeout is a very handy channel in that once 15 seconds have gone by, it will send a message to timeout, which will get returned, which means we've hit the timeout and we leave. So one of two things is going to happen as we sit here infinitely. We're either going to get messages or the timeout. If we get messages, they will simply get printed. But if we ever receive something from the timeout, which again can only happen after 15 total seconds, if we ever hit the timeout, we're just going to leave. And so now if we run this program, it's just going to sit here. It's going to eventually get all 4 responses, and then eventually the timeout will kick off after about 10 more seconds, so we'll just wait for that. And notice we're not getting a deadlock error anymore because we've explicitly said do not wait longer than 15 seconds total, so it'll eventually give up. Now an interesting thing can happen with timeouts. Remember that this slow file download, it's fake, but it's artificially waiting between 1 and 5 seconds. So what if we make the timeout 4 seconds? So it's going to try to download some stuff, but it only got these 2 before the timeout got hit, because our timeout again is 4 seconds. So this guy, Fedora, and this other one, Google, they are outside the timeout, so they won't be reached. So we instead hit the timeout. So basically when this program was running, these 4 Goroutines got started immediately. They're all running at the same time. One of them is going to take 1 second, then 4 seconds, 5 seconds, and 1 second. And we're just going to be sitting here infinitely listening for a result from the timeout. If something comes in, we're just going to print it, and then we'll continue listening forever. And we might get another message, print it, and continue listening forever. But eventually, we're going to hit the timeout, in which case we leave. And if we hit the timeout before something is done, then it's not going to be received. So we can run this again. This is going to take 3 seconds, 3 seconds, 5 seconds, 2 seconds. And so obviously because our timeout is 4 seconds, we're only going to get the results that took under 4 seconds. So Debian was the slowest at 5 seconds. That is outside the timeout, so it didn't come through. Only the fast servers came through. And so that's how you can use timeouts, or rather how you can use channels to selectively receive information from slow processes. So just to recap, you don't need an infinite loop. If all you want is first past the post, the first person that returns a result, you just use a select block and you receive a message from some channel somewhere. What did I call it again? Whoever's first. And then just print it. And in this case, this is just going to get a single result. And as soon as anything sends a message here, it's just going to immediately leave, because it's not in an infinite loop. It's only going to wait for a single message. So that can be helpful if you just want, for example, the fastest mirror from a list of servers, or the first search result from 4 different searches, whichever one comes back first. You don't need to wait for all the other ones. And if you want to continue to listen for messages because you're expecting to get a lot of results back, you can put it in an infinite loop and listen forever. But you have to make sure that you include a timeout so that you don't wait forever. Oh, it helps if you put this in the right block. I do that every time. You always need to include a timeout so that you don't just sit here waiting forever. This piece here will break us out of the infinite loop. And so those are the three different ways to accomplish this same sort of wait for slow going processes. And it's also a way of passing messages with channels. One other tiny note is that when you use channels as parameters in functions, because notice that we're never reading from this channel, we're only writing to it, I can mark this as a write-only channel by including this little notation, which basically says succeeded is a channel that is send-only of type string, which denotes that we can only write to that channel. We can't read from it. So if somewhere else I wanted to read from it, like message is defined to be receive from succeeded, this is just going to throw a compile time error because you can't receive on a send-only channel. But that's a very small note. It's not critical for how this function works. So hopefully that makes sense.